Our second speaker of the after break session is Professor Raffaella Margutti from Northwestern University. She's going to talk to us about transient sources and high energy emission from them.
All right, so thank you very much for having me here. So I've been asked to speak about high energy emission from transients, and it's kind of a huge topic. There are many, many transients in our universe, as you know, and each of them is important for different reasons. Type 1a supernovae are very important to measure distances. Stars, when they explode, they release into the environment all the chemical elements, so they're chemically rich of our universe. There is very important work on feedback from supernovae on their galaxies, and of course, what is important and relevant here is that when stars explode, they do produce the most extreme objects in our universe, like neutron stars and black holes, and while doing so, they might also produce very high energy emission and neutrinos and gravitational waves, as we know right now. As I said, speaking about transients is kind of a huge topic, so unfortunately I had to just decide, so I'll cherry pick a few of the possible things I will speak about. So I will I will spend a little amount of time on tidal disruption events, and then I will go quickly through the topic of gamma ray bursts and engine-driven supernovae. But today, the message that I would like to convey is that there is actually a new class of supernova explosions that might be very good targets to look for neutrinos and high energy emission. And those are what I call strongly interacting supernovae. And this topic is very much connected to the new class of explosions that we just found, those which are the most luminous supernovae known, the superluminous supernovae. So let me just start with tidal disruption events. Apart from inspiring a lot of artists with this kind of images, tidal disruption events are maybe one of the most exciting transients that we are now able to discover. And we do know that they arise from the disruption of a star when the star just gets too close to a supermassive black hole. And we do know that sometimes these kind of events are also able to launch relativistic jets. Maybe a fraction of 10% of these tidal disruption events can launch relativistic jets, which are a source of high energy emission. What I find remarkable is that in a few cases, we were able to witness both the birth of the jet, but also the time when the jet shut off here. And even more remarkable, I think, is that by studying the emission from tidal disruption events across the spectrum, so all the ways from hard X-rays to the radio, we are able to understand and map the density around supermassive black holes down to a level of precision that is actually better than in our own galaxy, which I find really remarkable. And if you are interested in the properties, X-ray properties of tidal disruption events, I really want you to draw your attention to a couple of papers by Katie, one of our organizers. And those are papers where you will find everything about the X-ray properties of tidal disruption events compared to AGNs and compared to other transients as well. We already heard today about gamma ray bursts. Gamma ray bursts have been mentioned already as possible sources of neutrinos. And I like to speak about gamma ray bursts and engine-driven supernovae. When I say engine-driven supernova, I mean any single time you need some extra ingredient to power your explosion, I call it an engine, which might manifest itself through a jet, for example. And a few years ago, the gamma ray burst field got very, very excited about the limits the IceCube was putting on neutrinos from gamma ray bursts. And I remember I come from the gamma ray burst field myself, so when this result was published, we all got very excited because for the first time, we thought, okay, the limits are constraining. However, if you do a more careful analysis, and here our chair is the expert, and you consider the fact that in a gamma ray burst you might have different shells colliding, not only one single shell, then the result is that these limits are actually not as constraining. But even more remarkable, I believe, is that Mauricio pointed out that actually this this more complicated picture gives us a very powerful tool because neutrinos and high energy emission actually rise from different regions of the fireball. So this means that if we can do a careful job, if we can do a good job, and if we can detect this kind of emission, we can actually probe what is going on in the fireball at different distances. So let me just now switch gear into what is the focus of my talk today. It is this new class of strongly interacting supernovae, something that has been recognized as a class only recently in the last few years. Let me give you some context to start with. So why should we care about supernovae, which are not gamma ray bursts? So why am I here telling you something about this other class of supernovae? If you draw a plot of kinetic energy versus velocity of a typical supernova explosion, you will find out that most of the energy is emitted in the optical, 10 to 51 ergs, a typical 10 to 51 ergs, and only little tiny amount of energy is actually carried out by the fastest moving ejecta in the high energy part of the spectrum. So the question is, why should I care if I only have way less than 1% of energy that goes here? So in the remaining of this talk, I'll try to make the case that actually there is a possibility to learn a lot, even if the amount of energy that is carried by this fastest ejecta is so tiny. So I'll try to tell you, I'll try to convey the message from this talk by telling you the story of two supernovae. And I'll tell you the story about supernova 2009 IP and 14C. So let me start with 09 IP. So 09 IP is a supernova that was, it was a transient that was discovered in 2009. And that was back to the time when in the supernova field you didn't need a spectroscopic classification, accurate spectroscopic classification to call something a supernova. So it was called supernova. However, from the very same location in the sky, and this is a very nearby galaxy, so we can really point at the location in the sky, the very same location in the sky, the very same star experienced outbursts in 2010. And the same thing happened in 2011, and we had two major explosions in 2012. So it's very clear that what was called supernova in 2009 was not actually a supernova. So it was renamed supernova imposter in 2010. And the star actually went supernova most likely only in 2012. So here is just a zoom in on the eruptions experienced by the star before the main explosion. And here is just for you to appreciate the presence of this precursor of emission before the supernova explosion. Just to give you an idea of how much energy is there, is not tiny. We have 10 to 48 ergs irradiated in the precursor and the usual 10 to 49 ergs or more in the supernova. So why is this interesting? So everybody in the supernova community got super excited. Why was that the case? Well, if we go back to a very hyper-simplified version of stellar evolution, this is what we would have expected from a massive star. Our expectation was that after becoming supergiant, we'd have to go through a phase called luminous blue variable star. And during that phase, we can expect to have eruptions. But after that, we are expected to spend 10 to 5 years in a Wolf-Rayet phase, which means very quiet, the mass is lost through winds, no outbursts. And only after that, we are supposed to explode as a supernova. We always got green light on this kind of sequence. The reason being that we were not covering this portion of the parameter space in the supernova evolution. However, things changed in the recent years because we have surveys that can monitor the sky every single night. So we do have data that tells us what the star was doing before experiencing death, stellar death here. And we do know that stars experience a lot of eruptions before dying, this kind of outbursts here. Every single eruption means that the star is releasing into the environment a lot of material. So you can imagine that when the supernova shock, when the supernova explodes, this shock has to go through all of these shells of material, which is the main reason why this kind of transients might be sources of high energy emission. So yeah, so you might stop and think about and ask me, well, why you're here at TeVPA telling us the story about massive stars ejecting their mass. And the reason being is the following. So in most supernovae, what happens is that you have a shock that goes through an environment that is mostly clean. So nothing happens, you propagate through that. What is happening here when the stars instead experience eruptions before is that the shock is all of a sudden crashing against a wall of material. So a lot of kinetic energy now can be transformed into radiation and released into radiation. And this is the reason why this kind of strongly interacting shocks, in principle, have the opportunity to accelerate particles, produce gamma rays, and maybe also neutrinos. There is actually a beautiful paper by Kota Murase about that gives you all the theory behind. So here's the thing, though. Once the supernova 2009 IP happened, people thought, okay, I can see from pre-explosion images, I can see the progenitor, I can see the star that did that. And if you do number, it turns out that it's a very massive star that produces this kind of eruption. So most of us in the community thought, well, maybe we do have stars that experience this kind of outburst, but it's not common. So maybe it's something that it is only happening in very massive stars, so they are a very, very tiny portion of the stellar population, so at the end of the day, why should I care? So in the next 10 minutes, I'll try to convince you that this is actually not the case, that these kind of eruptions are common in massive stars, which means that when a supernova happens, a lot of times, in a number of cases, you will have a shock that is going to go through this very high density medium. So let me now tell you the story of the other supernova, a supernova 14C. And we will see how strong interaction builds up in real time. And we were going to see it, we're going to witness this kind of thing all the way from hard X-rays to radio. So this theme of enhanced and episodic mass loss in massive stars is actually catching a lot of attention in the community, and there are many, many observations that support the notion that many massive stars experience this kind of outburst. And I showed you before that for 09IP, we could see really with our eyes, with the telescope eyes, these kind of eruptions. But there are many other ways you can infer the presence of shells around massive stars that I don't have time to cover. But if you're interested, please ask me about. The method that I'm mostly interested about today is the shock interaction with the medium. So here is, in a nutshell, here is what happens and how it works. We have a supernova. The shock expands and probes different regions in the density profile. And this density profile was created by our star before dying. And this is the source of, potential source of radio and X-rays and even higher energy radiation. So the basic idea is that if we monitor shocks from massive stars at their explosion, and if the medium, instead of being a beautiful, smooth power law, is instead made up of different shells, the idea is that by monitoring radiation that comes out from this shock, we would be able to learn about the environment of these massive stars as well. So with this idea in mind, I tell you the story of a supernova. And I think that each of us at grad school was taught that supernovae are classified into two main classes. You can either be type 1 or type 2, yes hydrogen or no hydrogen. And here is an example where we witnessed for the first time a supernova that transitioned all the way from one class to the other, from type 1 to type 2. And this is the result of the shock interacting with a lot of material in the environment. So here is the story. 2014C is a very close by supernova, 15 megaparsecs. And here I don't care about details. The important thing to take away from this slide is that if you had a look at this supernova at early times in the optical, it looks normal. So the red line and the black line is an optical spectrum, but what I care about is that they track one another, and they look the same. And in red, you have a stereotypical type 1b supernova. You look at the energetics in the optical, and it looks normal again. So the bottom line from this slide is that in the optical, the supernova looks normal. This is extremely important because it means that normal supernovae can do what 14C did, and maybe we were just not paying enough attention before. So, however, if you keep staring at this supernova, you will notice that something happens, even in the optical. And I know most of you are not optical astronomers, but just bear with me here. So, what happens here is that in the spectrum, you build up hydrogen. This is something that does not happen in most supernovae. While this is happening, let's see what is happening instead on the other side of the spectrum in the radio. So here is a plot of radial luminosity versus time for the entire world of hydrogen strip supernovae. And just to put you into context, consider that we have 40,000 supernovae detected in the optical. We have 33 detected in the radio. It's very different. And in the X-rays, it's even more pathetic, I would say. So here is how 14C compares. So what you're going to see, what you notice right away is that this supernova shows a late time rise in the radio. So let's do the same exercise, and let's use instead X-rays. And what you will see is that, again, this supernova rises in the X-rays, which is something that you would not expect. Even more to this point, the spectrum of this supernova in the X-rays was very strange. It was hard spectrum. In the Chandra, passband was even rising, which motivated us to request Nusser observations of this supernova. And what you're looking at here is actually the first image of an extragalactic hydrogen-stripped supernova, young supernova, at these energies. It's kind of, remarkable. And here is, people got very excited, and here is how it looks when you have great people working with you and making beautiful images for a press release. So let's put everything together and see what is going on, and let's see why is that important, why is that relevant here. So what I told you is that I had a supernova that with time changed flavor and went from type 1 to type 2, building up hydrogen. And the radio and X-rays luminosities were rising with time, which is unusual. You would expect it to slow down. So what is happening here? What is the physics that is causing this kind of behavior? What is happening in very oversimplified picture is the following. You have a supernova that at the beginning looked normal. The shock was sampling a very, very normal environment. However, at some point, and this environment was hydrogen poor, so it looked like normal. However, at some point, the shock encountered a high density wall of hydrogen-rich material. And this is what caused the total metamorphosis from type 1 to type 2 supernova. This is what is causing the X-rays to go up instead of going down. This is what is causing the radio to go up instead of going down. So even more importantly, thanks to the monitoring that we did we're still doing combining Chandra and Nusser, we were able, for the first time, to really constrain the spectrum. It's a beautiful Bremsstrahlung spectrum. So we could constrain the evolution of the temperature with time and the evolution of the absorption with time. So why is that exciting? Because temperature speaks to the shock velocity. Absorption speaks to the amount of material in front of me. So combining this kind of analysis, I can actually infer the properties of the environment. So I can understand where was the amount of material and how much it was. And this is just to tell you that by monitoring different parts of the spectrum, you actually get different emission processes playing a key role, which gives us the possibility to constrain the physics behind. So what we were able to do is that we could infer that as much as 1 solar mass of material, of hydrogen-rich material, is contained in a wall of hydrogen. It was sitting very close by to my massive star at the time of death. So 5 × 10⁶ centimeters is very close by. So let's go back and see why is that relevant at all. So here is our expectation. Here is what we're finding. So you understand that even from the perspective of stellar evolution, this is sending us a strong message that we are missing some key ingredients there. And if you're interested, to know a little bit more about what is the reason why we have this wall of hydrogen, well, I can tell you, without going into much details, that is most likely related to the presence of a companion of the massive star at the end of life, or to the presence of nuclear burning instabilities that are happening at very late time in the massive star itself. However, what is interesting here is that this is not a unique behavior. So it's not that 14C and 09IP are weirdos. This is something that we can say that happens at the very least in 10% of hydrogen-stripped supernovae. So you have 10% of supernovae, which are the so-called type 2Ns, which do experience this kind of behavior by definition, plus this other 10%. So it's something that is pretty common among massive stars. This is just to remind you how it should look like in radio. Yeah. So why is that relevant at all here? Because we believe that these strongly interacting supernova shocks might be good sources for your high-energy photons and also neutrinos. And again, if you're interested, I refer to this beautiful paper by Kota here. So all of these stars, all of these supernova that I plotted here, they share one thing. They all crash against a lot of material. So they do have this possibility of converting a lot of kinetic energy into radiation. What you're looking at here, I'm sure you're already noticing that we have a bunch of lower luminosity, these magnitudes, but we also have some extremely luminous supernovae, which allows me to go into transition to the last part of the talk, which is about superluminous supernovae in the last few minutes. So if you were to ask to any supernova person until a few years ago, what is the most luminous supernova known, hydrogen-stripped, they would have told you, well, there are those that are connected to gamma ray bursts. And that would have been an accurate answer. However, in 2011, we were able to identify a totally new class of supernovae called superluminous supernovae, which are all the way from 10 times to 100 times more luminous than ordinary supernovae. And the main question that we have in the field is very simple. So what is the source of energy that is powering this supernovae? And just to give you an idea, here for superluminous supernovae, the radiated energy is 10 to the 51 erg. So not the kinetic one, the radiated. If you just measure what you got in photons, it's 10 to the 51, and maybe even more. So the main question is the simplest you can think about. So what is powering this supernovae? And it turns out that one of the possibilities that are out there is that we can power this extremely luminous supernovae with strong interaction. So again, the idea is that your supernova explode in a very polluted environment. So you have the possibility to be extremely more efficient in converting your kinetic energy into radiation. The other main contender that is out there is a magnetar model. So in this case, instead, the idea is that the star collapses not directly to a black hole, but forms a magnetar. The magnetar has some rotational energy that you can think that maybe we can use to power the supernova. How that happens is a big mystery. The relevant thing here is that by monitoring superluminous supernovae, if they happen in the nearby universe especially, in the high energy gamma rays, we might be able to distinguish between interaction and magnetar. This is one of the possibilities that we have right now. So here is just a concluding slide. I hope I have convinced you that you might have a new source you might want to keep an eye on, which are the strongly interacting supernovae. Those, in principle, if we were able to detect the gamma rays from these sources, we would be able to learn a lot about the environment. So that would be relevant for people who care about stellar evolution. But it has also been suggested that maybe these kind of shocks might be also able to accelerate cosmic rays. And I'm very happy to say that for 14C, we were actually able to get Veritas observations, and the analysis is in progress, so stay tuned. And that's it. Thank you.
Can you use the mic, please? Because otherwise it doesn't go in the video.
So I guess the question was, what was the mosquito? Because the energy of a mosquito is around 1 TeV.
All right. Any other question? Insect related or not? I don't see any hands right now. Oh, there's one. Okay.
In Kota's first paper and his second paper, he indicated that if protons were being accelerated, then the secondary electrons and positrons from pion production could radiate in the submillimeter band.
Yes.
And I was wondering whether to date there have been limits or detections or follow-up with ALMA or any other submillimeter telescope.
Great question, Todd. For TNC, we are doing ALMA follow-up, and we might have a detection of exactly what you're saying. And the complication being that the spectrum is not particularly well behaved, and we might have contamination. But yes, that is, for TNC is the best case, and we have been getting ALMA since 2 years. Yeah. So yeah.
Have time for another question? I have one curiosity. So when you're trying to find these oddly behaving supernova, do you actually look for them in places that you know should be polluted?
We do look at that in the optical, because that's the cheapest wavelength you can go after. And then when you have interaction, you produce very peculiar narrow lines with velocities which are 100 kilometers per second, which tells you that interaction is happening. And when that happens, then we trigger all the other follow-up, which quantifies how much matter and where it is. Okay. That's the way we do it, yeah.
Makes sense. All right, well, let's thank Raffaella again.